Okay, so here we are in the second part of our wood design lectures. Last week we looked at sizing guidelines with wood and basic construction methods with wood. This week what we're going to talk about is the actual design of wood. Now, I'm trying to keep the format as similar to the steel method as possible so that you can see kind of how they evolve together. Now, what you should know is that there was a bunch of really smart people developing equations over here for steel, and there was a bunch of really smart people developing equations over here for wood. So they don't look the same at first glance. But I'm going to show you that if you break it down and talk about it in a very simple way, that the equations are actually almost identical. Wood has a few hiccups though. Steel is this beautiful thing that we make in a controlled shop. As much as it's big and messy and loud and hot, it's actually very precise. It's a very precise science how we make steel. And there's actually a chemist in every steel plant making steel. Wood, we go out and cut it down in the forest. So we don't have a lot of control over the product we're getting. So we have to build that into our design. But it's a wonderful, easily accessible, strong material, or strong if we design with it correctly. So because last week we introduced the whole concept of design with these elements, this week with wood, we're going to spend a lot of time talking about the fact that wood is an organic material that we grow, and we need some way to talk about it. But the same way we did with steel, I'm going to show you what all the equations are, and then I'm going to show you the tables that you can use to actually replicate those examples. It's going to be slightly more obvious why I would bother to teach you the complex equations at all if you're always going to have those tables to look it up, because we're actually going to look at one where the tables might not be that handy, or they're handy, but they get us most of the way to the answer. And it's a good place to start, and it's why I wanted to show you it in this particular way. It's already been a week for me. Like, it's been a crazy week. I've had 3 projects come back to life that were on hold. One of them is a large-scale project that took me by surprise that they decided to start the project back up again. One of the other projects they've just started building without any communication. So I am exhausted. I will try not to muddle my words up too much. On another note, a thing that had been on my wish list to solve for a while was making the pointer bigger. For whatever reason, with the software that screen captures, the mouse will grow on my screen as I increase it incrementally, but it won't show up on the software for whatever reason, unless I make it gigantic. So the only option is this gigantic. You can see the little tiny dot just at the tip of it. That's all that shows up unless I get it into the gigantic phase. So this is the very gigantic pointer we're going to use, but hopefully that's a little bit easier for you guys to see kind of what I'm referencing on the screen. I don't think we need to do any side breakout calculations. The calculations are all very, very simple in this lecture, so I think we can do it just on the screen where you can see me talk through it with the pointer. So what's the dealio with wood? Wood is an organic material that we grow when we go and cut down in the woods, which is what I've kind of mentioned already. Obviously, you'd have to have some understanding of wood to know how we could possibly design with it and categorize its strength. You probably all remember back to a very young age where you talked about hardwoods and softwoods, which almost always break out into deciduous and coniferous categories. My 4-year-old this summer was obsessed with classifying deciduous and coniferous trees from each other, especially once I taught him that spruce tip needles are edible, especially the tender ones in the very early spring. So we spent a lot of time eating spruce tips all summer. Hardwoods are almost always deciduous trees. Not always, but usually they're deciduous trees. So those are the leafy ones that, if you look outside, have caused no end of headache for everyone who's trying to rake. So they shed their leaves at the end of the growing season. Softwoods are almost always coniferous trees. They're the cone-bearing ones with needles. Most coniferous trees keep their leaves, which are needles, throughout the winter, giving them that classic name, evergreens. Most lumber that we use comes from softwoods. So if I asked you, what is the type of wood, or what do we use, hardwoods or softwoods for most of our construction wood, the answer would be softwoods. We are starting to use poplar and aspen more for our parallel strand lumber and our laminated veneer lumber, or our LVL and our PSL. But those make up such a small quantity of the construction material we use that mostly we use softwoods. They regrow nicely. We can control their growth a little bit. Back in the day, we did love to use hardwoods, but we weren't very good at managing ourselves. And we cut them all down, cut down all the good ones, and they take a long time to grow. So the softwoods, there's a lot there. We can replant them easily, and they regrow easily. So softwoods are the majority of our construction material. There are 30 types of common softwoods in Canada, but we only stick to 4 of them as the ones we tend to use the most for our construction material. So spruce, we use a lot for our dimensional lumber. 2x4s, 2x6s, 2x8s, 2x10s, 2x12s, 4x4s, 6x6s. They are nice and cheap, they're easy to get. So spruce is the one that you're often getting, especially here in Ontario. We're going to see in a second that it gets categorized with a few other types of materials, because across Canada there's slightly different accessibility for different materials, but mostly our 2x material is spruce. Pine we use more for trim work. Cedar is really good for decks. We love cedar outside. It's got natural basically internal chemicals that help resist rot and bugs. You can imagine bugs love to eat wood. Cedar, if you've ever worked with cedar, when you cut it, you know that distinctive scent. The cedar trees have that naturally in them, and bugs tend not to like it. Douglas fir grows great out west, and we tend to use it for the big scale things. So think glulam materials, or our kind of big made products. So all of those different types of woods get broken up into different categories. Now, there are more in here than I listed than those common 4, and sometimes those 4 jump around in the different categories. But this is how we break out species combinations for strength properties. So these are the species of structural wood that we commonly use for construction. This is the species combinations that we would use to talk about wood properties. Douglas fir larch, or D fir L. Hem fir, this one, I don't use this very often. Hemlock's really good in the water. I've used hemlock for kind of high-end docks some, but that's about it. SPF, spruce pine fir. Remember I said that spruce is our most common one, or let's go back and look here. Yeah, spruce here was our most common one for 2x4s. Well, then the category that has spruce in it, or SPF, is going to be the common one that we use for construction. In fact, when you go into Home Depot, it's usually got a stamp on it that says SPF. That is saying that it is spruce pine fir category. And the northern species is where we lump our cedars. So if you're talking about designing with cedar, you're talking about the northern species. And that's going to come back into play in a minute. So just kind of a refresher on what a tree looks like and why it might be important, and why we'd bother to even talk about some of this stuff. This is the cross-section of a tree. You can see that we've got the heartwood is the center spot. So that's the stuff that grew in the past. It tends to be very dense and hard. The outer layers of growth are the sapwood. So that's where we actually have sap moving up and down the trees. If you have a sugar maple, this is where you put your tap into to tap your sap to get syrup. Trees, you all know, grow in rings that designate a year of growth. We're going to look at a slide in a second that shows that really well. The outer bark, inner bark, and then all of these lines in it are piths or rays. The summer wood is a denser growth ring, and the spring wood is a larger growth ring. So basically our wood grows really fast in the spring, and then it slows down over the summer, and essentially comes to a dead stop in the fall and winter. And then spring comes and we get rapid growth again. It shows really well in this image here, where you can see we've got the cellular structure where the spring wood is growing very fast and it slows down in the summer, and then here's where we've hit the fall and we don't really get any growth until spring comes again. So actually I want to look at this again. You can imagine that if you had a bundle of straws in your hand, how they behave trying to squash them versus how they trying to squash them versus how they behave trying to bend would all be very different depending on what direction you were talking about. You can imagine that that straw-like structural component of cellular structure could greatly vary the way it behaves. Our steel was isotropic. Isotropic means it behaves the same in every direction. It doesn't matter if we're squashing it this way or squashing it this way or squashing it this way. It behaves the same. Our wood is heavily dependent on what direction we're talking about. So wood has a few other quirky things going on with it. It's got moisture. There's water content in our wood. When we cut it down, in fact, I had a sugar maple fall in my front yard this late August. I guess it was maybe early August. And it came down late on a Friday night. We had an emergency arborist come in, and they said, for $1,000, we'll cut it down, but we're just going to leave it in a heap in your front yard. So we've been slowly dealing with that, and I have a friend who's an artist who paints discs for Christmas ornaments. So I've been slicing discs for her to paint. And even though it's been sitting there in my front yard since August, so August, September, October, 3 months of sitting there, when I cut, you can see the moisture in it. The ones that I cut in September, very wet still. The ones I'm cutting now, you can see have dried out quite a bit. But if I set it down on the table, it'll actually leave a bit of a moisture ring. So I think I cut her. It was nice yesterday. I cut her 100 and some discs to paint. Wood shrinks. So as it dries out, it actually shrinks. That cell structure loses the moisture that's inside it, and it actually starts to shrink down. If we have a house, for example, over a story height, you might get a 1/4 inch of shrinkage. Usually not that big a deal in house construction. There's lots of alternate load paths, we've nailed things together, but I've been in old houses where I've gone down in the basement and the posts have shrunk, and the posts actually aren't even sitting on their bearing support in the basement. You can kind of feel them and they move around. If you're building a 14-story building, that equals 3.5 inches of shrinkage. So you can imagine that starts to have a really big impact on the way we design. We have to take that into consideration and think about how that would work into our engineering. Like I said, it's non-isotropic, which means it is not the same in every direction. It changes its behavior in each direction. It's not perfect. There's lots of natural imperfections. It has trees that grow into the side of it, so there are knots in it. That can change its behavior. You saw those checks and rays in it. That can change the way its behavior is, or it's got basically cracks in it. Wood creeps. If we load up a piece of wood and do nothing to it, and this is independent of the shrinkage, if it's got a load on it, it will slowly deform and stay that way. So this has nothing to do with elasticity, and it has nothing to do with shrinkage. It will naturally bend somewhat to take on that permanent form. It's not a lot, but it's something we need to consider in our design. Wood, again, is an organic material. It is susceptible to rot, and it can be eaten. So that's where we might need to do treatments on our wood to preserve it. I'm so tired, I was wondering where the slides were that tell you what you can and can't build with wood and its strengths and its weaknesses. And then I realized we did that last week. That was a whole lecture that I gave you guys last week. The other thing is that it burns. We know that if it's big enough, it might not burn badly, or it will burn and it'll build up a layer of char and we're left with structure in the middle, but it is combustible. So remember, there's combustible, non-combustible, but then there's fire rating, which is a separate category. So wood is combustible, it will burn. So if we think of that chart there, we can start to take those things into account and think about how we can build that into our wood design. I'm going to take out my trusty foam block because it might come in handy. So we build into our factors for wood the fact that there are different species of woods. We grade our wood. We have a grade category, and I'll show you those in a minute. That one really takes showing you to really make you understand what's happening there. Size. Size can change the effect of wood. The likelihood of shrinking, the likelihood of having a knot in the object changes depending on its size. Also being able to visually grade it, if it's small enough we can see all of it. If it's big, there might be a flaw inside we can't see. System effects. So system effects are interesting, and I'm going to show you a slide about system effects in a minute. But basically that's saying if we have a lot of the same thing doing the same job, they can kind of help each other out. Load duration can have an impact on our strength. Remember that creep thing? That's where we talk about load duration. Service conditions, wet versus dry, would talk about rot. Chemicals or preservatives for rot and fire treatment. And then the one we talked about last week was steel, which we built into our steel. The only one of all of this list that we had for steel was lateral stability or buckling factor. Remember that tendency to buckle if it's in compression, or for the compression side to pop out sideways if it's in bending. The only factor we had in steel was that lateral stability one, whether it was compression or whether it was in bending. But we still have that for wood, and we have to think about all of these things when we talk about wood. So let's look at all of those. So this is the visual grades and their dimensions of wood. So here's a grade category, and we've broken it up into light framing, stud, structural light framing, structural joists and planks, beams and stringers, posts and timbers, and then plank decking. All of these different types of things have different charts for the strength. But then look, we also have a grade as well, whether it is select structural, number 1, number 2, or number 3, or even a stud grade. So these are all visual gradings of our lumber. So literally, wood goes down a chart, goes down a conveyor belt, and somebody stands there and looks at it and says, that looks good, it's select structural, that one's crap, it's stud, that one's okay, it's number 1 or it's number 2. So select structural is the one that looks the best. It has very few knots in it, it has very few checks, very few flaws. If your wood is exposed, you might as well use select structural because it's probably the one you want to use. If it's hidden away, we're probably going to talk about number 1, number 2, or number 3, or even stud, unless we need something nice and strong. Because select structural, as well as looking good, is going to behave better. I'm going to show you some charts with these. And then here are the ways we can help figure out which grade category we need to talk about. It talks about dimensions here, and we talk about relative dimensions. So again, this is a pain in the ass to understand on its own. The best thing to do is for me to show you all of the charts, and then we'll actually do an example. So there are multiple, well, for each one of these grade categories, there is a strength and modulus of elasticity table. I have given you all of these in a sawn lumber list because these all apply to sawn lumber. I'm gonna show you tables for glulam, but I'm not gonna go through the strength and modulus of elasticity of the glulam ones. So you can see here that this is a grade category for structural joist and plank, structural light framing, and stud grade categories of lumber. And then down here, we've got our species identification. Here we've got our grade, so SS is select structural, number 1 or number 2, number 3 or stud. And then look at this, FB. Remember for steel, our stress, we called it FY because it yielded. Well, wood doesn't yield. Wood is brittle. It has no plastic zone. When we hit the end of our elastic zone, it fails. And that is listed here as FB, or the strength or the stress at which it fails. And these values are all in MPa. So spruce pine fir, I said, is the most common one. Number 1, number 2 tends to be what you go buy at Home Depot. For bending, FB is 11.8 MPa. Remember our steel was 345 or 350 MPa? So we are a fraction of that, like 35 times less strength. Unless we're talking about shear, which only has 1.5 MPa. And then compression parallel to the grain. So if we have our piece of wood like this, all of our lines run this way, or basically our cluster of straws. This would look like going to McDonald's where we have a stack of straws, and here would be all the holes that you could see. Well, that would be compression parallel to the grain, or 11.5 MPa. So those are the main ones we're talking about right here. They also give modulus of elasticity. Don't worry about E or E05. That's a whole thing. It's basically saying it's a percentage of this. If you looked at standard deviation and how much of it was off of the mean. But this is just talking about the stiffness of the material. So for our most common type of lumber, which is spruce pine fir, number 1, number 2, bending at for a joist or a stud, remember a beam would be something different. We're going to look, that would be a different grading category, and I'm going to show you that in a minute. But for a joist or a stud, our bending would be 11.8 MPa, our shear would be 1.5 MPa, and our compression strength would be 11.5 MPa. And then we have modulus of elasticity over here. Well, what if we didn't have joists or studs? What if we had light framing? Again, this one we're not going to use. Don't worry about this one. I just wanted to show you that this one exists. Here's our beam and stringer grades. So these are what we would call a beam. This one was what we would call our joists, similar to our purlins in steel. And then this would be our beam category. So look, we've still got Douglas fir, hem fir, spruce pine fir, and northern. Look, they've broken out number 1 and number 2 from each other. Before number 1 and number 2 for our joists, it was the same category. Look, bending at extreme fiber, if it was number 1, number 2 for joists, it was 11.8. Look at the difference here for bending for a beam. Our shear goes down, and our strength compression parallel to the grain. So we have different strengths depending on what direction it's going in, depending on what species of wood it is, and depending on what job the wood is doing. So for steel, it was just 350 MPa, 345 if it was hot rolled. But I've already shown you just one type of species, and there were already 6 different values. Look at all the different values depending on what it's doing. And then we also have our post and timber grades, so there's even more. Look at our spruce pine fir number 1, number 2 in bending now, or our compression parallel to grain. So we have to know what species we're talking about, what grade we're talking about, what job it's doing, and then what type of load we're trying to resist, and then we can figure out what our strength is. But we don't stop there. It goes even further. Then we need to add in our factors that change the way we might categorize that strength, or that strength we might have pulled out of those tables. So we've gotten that far. We know we've got, a Douglas fir select structural beam. So we can go pull off our bending strength. But then we still have all the factors for the fact that this is wood. There's a short-term duration factor, which actually increases the strength of wood. So that would be for wind, earthquake, false work, or formwork. Basically, the wind is on there for a very short period of time. But most of the time, we're talking about standard term load durations. So that says examples include snow, live loads due to occupancy, wheel loads, and dead loads in combination with any of those other loads. So most of the time, our KD is 1. System factor. Again, I'm not actually going to make you use any of these, but it's important that you understand where they come from. The way we grade our wood is usually a visually graded lumber, which is listed right here, which is, I said, it goes through the conveyor belt and somebody says that's type 1, or that's number 1, that's select structural, that's stud grade. Not part of a system is something doing a job all by itself. So a beam, a column, those are doing a job all by itself. Systems, it should just basically say, we're talking about joists and studs here. The thing that happens very often, or around 16 inches on center. Remember last week our joists and our studs were about 16 inches on center most of the time? Well, that's starting to talk about a system. And if you want to think about it this way, if I have, go over a life cycle of an apple chart here so I can draw on it for you. If I have a series of joists at 16 inches on center, like this, and I stand with all of my weight on one joist, that joist isn't part of a system and it's doing all the work by itself. But we know that joists are usually supporting deck. So if we put that deck on this, if I stand right here on this joist tries to go down, but it brings the deck along with it. And for the deck to go down, it has to engage these two joists just a tiny little bit. And that is what a system factor is. So, no system, our system factor is 1. It's all by itself. But if it's part of a system, we get to increase its strength just the teeniest, tiniest little bit. And that is this chart right here. Here's the explanation of what a system is. So a case 2, specified strength for sawn lumber used in a system of joists, rafters, studs, meeting this clause here, which said that they were less than 6'10" apart, or less than 20 inches apart, 24 inches apart, sorry, less than 24 inches apart, which 16 inches is, and it's got decking of some sort on it, and it's connected in some way, and I'm going to tell you that these are all pretty standard ways of building this. We've got our plywood on our joists at 16 inches on center, means it's case 2, which means that for bending, we can increase our strength by 40%. So we're saying that we're getting 20% of this guy and 20% of that guy added into this one right here, just for free, because we've already built this system into it. We needed it. We didn't do anything extra, but once it's there, we might as well use it. Service condition. If it is a dry service condition, 1. So that is basically anything inside an envelope. If it's outside an envelope, we have to consider that it's wet. Even a soffit on the underside of a ceiling, so a front entryway that has a soffit, we would still say rain could splash under there and get it wet. Decks, definitely wet. A surprise one is pool conditions. So if you're building a roof over a pool, even if it's inside an envelope, if you've ever gone swimming at a community center pool, there is a lot of moisture in the air, and they consider that a wet environment. So if that was a wood ceiling, we'd use a wet service condition, or maybe we have decking on it, we would use the wet service condition for that. Treatment factor. So if we need to apply something to our wood because it's in a wet condition, we would have to take that into consideration. Now, there's a fire retardant treatment that can be applied that I can tell you I have never used for wood. Ever, ever, ever. I know there are times where this has been used, but it is so rare that I haven't used it. And I've done mass timber things, I've done residential things, I've done decks. But this is not a normal thing. And there's in-depth calculation that you would do for this. So don't worry about this, but there is a fire retardant we can put on things. So if you've ever gone into Home Depot to buy wood for a deck, you've either bought cedar or you've bought pressure-treated lumber. And pressure-treated is the treatment we're talking about most of the time here. So a dry service condition, when it's untreated lumber, dry or wet, our treatment factor is 1. We've done nothing to it. There's no treatment applied. So dry or wet, our treatment factor is 1. It doesn't mean our service condition is 1. That was a different table. But if we have unincised pressure-treated lumber, dry or wet, it's still 1. So what happens there is we take our lumber like this, and they basically put it in a bath solution, and then they pressurize it. And if anyone's worked with pressure-treated lumber, it used to be very distinctive because it was green. Now they have a new method of pressure treating that uses actually fine copper particles in it. And so it ends up being the slightly brownish, I think they call it the micro sienna treatment. You know, when I started building a lot of decks 12 years ago, the green pressure treat was ubiquitous. You can actually barely find that anymore. It's almost all the brown pressure treat now. And so if you cut it, you will see that it looks like this. This is where the pressure treatment has gotten into it. So if it's dry or wet, it actually doesn't change the strength if it's unincised. So even though it's pressure treated, the strength stays the same, wet or dry, but we have to go back to the other slide for the wet service condition factor. But if you've ever bought some of that lumber and it looks like it's littered with staple holes, that's incising. And so basically what they're doing, and I've done it right here, I've shown that I've marked some holes there. That's where they've incised it, where they've basically gone and punctured these little holes in it. And then the pressure treatment, well, maybe it even goes in further than that. The pressure treatment goes in a lot further. But that decreases the strength of the lumber now. But it's going to hold up better in a wet environment. So this is where the trade-off is. You might need more lumber, but it will last longer because it's been pressure treated with incised, by incising it. So you can see here that if it's got an incised pressure treatment on it, we can see that we have our treatments go down. Interestingly enough, for other properties, the wet service condition is actually higher than the dry service condition, because it actually swells up a little bit and gets back some of its strength, which is kind of kooky and strange. We've got our pressure treatment there. There's another type of pressure treatment that's marine grade. I had a fish shack that finally sold in May. Yes. That my husband and I bought sight unseen 10 years ago, and it was wonderful and lovely, and we spent a lot of time there. But it was literally falling into the ground. There was a hole in the floor where you could see the tide go in and out. It was actually a working fisherman's wharf, not in the zone where there's been a lot of conflict recently in Nova Scotia. Look into it. The Mi'kmaq people are fighting for the rights to be able to fish as per their treaties. Very interesting stuff happening there. But this wharf, if this was my fish shack, you can see that, well, it's hard to see because you can kind of see the life cycle of an apple in the background. But you can see here that I have the building, here is the ground, and here's the water. Here was the building that actually came out on some posts like this, and here is the wharf. And this is, I won't draw it, but here's where the boats tie up. Now, if you know anything about Nova Scotia, it's got the highest tides in the world. So you can imagine that this water level goes up, and it goes down, and it goes up, and it goes down. And where things do the worst in water is where it gets wet and where it gets dry. If it's permanently in the water, wood's actually fantastic. If it's permanently out of the water, wood is fantastic. It's the getting wet and drying out, and the getting wet and drying out where we start to see a problem. So my stepmother went to the site and looked at it for us before we bought it for a ridiculously small amount of money, because like I said, there was holes all over the building. And we said, let's buy it. It's a fun lark. We'll develop it and turn it into something fun. We started it, and then we had kids, and then someone else bought the one next door and asked to buy ours. So we sold it, thankfully, just before all the hurricanes hit this season. But these posts right here were getting wet and getting dry. And in between us buying it and us getting to see it for the first time, the wharf was in the water at one corner. This is what happened. These logs that had been used to build that deck were actually wood that the first person who built it went into the woods in the back, cut down some trees, and just built their deck. They still had their bark on them. So what happened here is it actually rotted away, and there was nothing left. So this bottom piece fell over, and the upper piece, the deck, the wharf, tipped over and embedded in the water. And it was actually stable again. It went whoop and zipped down almost to the water, but it was stable again. So you could walk on it. So we ended up having to hoist it back up. I'll try to give you the hoisting video of that, just for fun. I might swear in it, so mute it if you're offended by swearing. Mute it. Like I said, I'm from Nova Scotia. I grew up beside where Trailer Park Boys was filmed. It's a way of life for me. I try to cut down filming the videos, but I didn't expect students to watch that video, so I'll try to post that hoisting video for you guys. Anyway, one of the things we did when we rebuilt it is we bought marine-grade pressure-treated lumber. So that anecdote, while it seemed completely random, talked about wet service conditions and how it can rot wood, and also marine-grade pressure treat. It was so heavy with the pressure-treated material that I could barely carry these pieces of wood. Now, they were 3x6s, so they were gigantic, and like 16 feet long, but I had a hard time moving them around, drilling through them, because we had to through bolt through them. I had to use, I couldn't use an impact driver. I had to use an actual normal driver, which if it catches wrong will take your wrist along with it and break your wrist. It was like trying to drill through goo, and it would bind up all the time. So that pressure treating material is intense, especially the marine grade stuff. Size factor. Basically, for a small piece of lumber, they figure you can see all the flaws. So we're going to increase for bending somewhat. Compression has another separate little clause for it, and it's actually an equation that I'll show you a minute in the compression slide. But for bending, we get to increase the strength. But as we get down into really large pieces of lumber, the fact that there could be a major knot hiding inside it that we can't see, the odds of that go up. So we actually decrease the strength a little bit for bending. So let's take a look at the compression design equation. Again, like steel, you're not going to have to use the equation, but I want you to see where it comes from. So the things we pulled off of those charts for the strength was a small FC or a small FB. So here is our compression. So pay attention to the lowercase or the uppercase. Resistance factor or our reduction factor for wood, I'm going to change that to say reduction factor. I don't like, I've always referred to it as a reduction factor up until now. I don't like that I'm saying resistance factor here. So I'm going to change that to reduction factor for you. Is 0.8. Remember for steel it was 0.9? Well, the wood, slightly more variability. So we're going to reduce the strength of wood just a little bit. Capital FC means that we've pulled off our strength or our modulus, our strength or our stress for our wood capacity, and then we've applied all of our factors. So KD was our duration, KH was our system factor, KS was our service condition, and KT was our treatment factor. So lowercase, without the factors applied, uppercase, with factors applied. That lowercase FC, that's the specified strength or the stress in compression parallel to grain that we would pull off of one of those 4 tables that I showed you first thing. Again, KD, KH, KS. This is the service condition for compression. and KT. So remember, our service condition one had different ones depending on if it was in bending or in compression. A, so that's our reduction factor. That's our strength with our factors applied. A is our cross-sectional area. So B times D for a rectangular section. That's nice and easy. We've got a rectangle, we've got B, and we've got D. Remember, B is what we call width, D is what we call depth. KZC, that is our size factor. So remember, for our beams, we pulled off KZ, so KZB or KZV for bending or shear. We actually pulled it from this table. And compression perpendicular to grain, it said there's a clause we look at. Well, that's this. That's just this equation right here, where it's 6.3 times the depth times the length to an exponent, but there's an upper bound on it of 1.3. Again, you're not going to have to calculate that, but the bigger it is, the more likely there's a flaw hiding inside it. And then KC is essentially our buckling factor, or what's the likelihood of it trying to pop out sideways when we put compression on it. Now, what we do with steel, it's pretty obvious. If you look at this, when I try to squash it, you can see that it tries to buckle in the direction of the thinnest dimension. Pretty obvious. But if I just put my finger right here and I don't do much to it, it's really hard to get it to buckle now. Remember our decks or our joists on our steel stopping it from buckling sideways at the top? Same thing. It does not take much to stop it from buckling. Wood, often, if we looked at studs in a wall, remember, we often, if this is an elevation of a wall and we've got studs here, we've often got blocking in between. So that is literally doing this. It's stopping it from buckling. You can see my buckling shape is actually changing here. So the question then is, it's not obvious if it's going to buckle in its weak or its strong axes, depending on if we have buckling. So this is all about unbraced length, so effective length associated with the width and the depth respectively. We check both, see which one's the worst, and then we plug a whole bunch of crap into this big, nasty equation. Remember in steel we had that lambda? This is almost identical to our lambda equation. See, look, we've got 1 plus a whole bunch of stuff with weird factors in it to a -1 or the inverse of it. It's almost identical to that lambda portion of our steel column equation. Again, you're not going to have to calculate it, but I want you to understand where it comes from. Look at this. We had, for wood, PR. PR is just another way of saying CR. We like to confuse you guys by changing up our letters that we use to talk about things all the time, but PR and CR talking about the same thing. So this is our wood equation that we just looked at, where we've got FC, which is just all the factors on our strength, our area, our size factor, and then this is all about buckling. Look at this. We have our lambdas, we have our areas, we have our strength. Steel didn't need any factors for the fact that it's steel because we made it. Wood, this uppercase F means that we've just applied all of the factors for the wood itself. KZC is just another factor that lumps into that. And then this KC looked very similar to this component of this equation. Another way to write it would be to say for that both of these are compressive resistance is our reduction factor times our strength capacity, or the stress where it fails, times our area, times a bunch of factors for whether it's wood and for buckling. Steel, there wasn't really any other factors but the buckling factor. Wood has some other factors and the factors for buckling. But look at this, the basic component of the equation stays the same no matter what. Reduction factor, maximum strength that we can see, our area, and buckling. Here is a compressive resistance chart for a column. This is the same thing I showed you for our steel one. Here's where if it's not governed by buckling. This is its strength, no matter its length, if it can't buckle. If it can buckle, here's the critical load depending on height. And then the actual compressive resistance varies depending on if it's short or if it's long. Over here, if it's short enough, it could only be governed by squashing. And as we get taller and taller and taller, the fact that it's going to buckle becomes more into play until we hit a limit where we say, no way, even if you can calculate it, it's so slender and it's so flimsy, we don't even want you to use it. We've put a hard line on there. There's a limit on that. So let's look at an example of compressive resistance, or let's look at the compressive capacity of an 89 by 89 wood post that's 2.6 meters long in an interior environment. The wood is SPF number 1 or SPF number 2, and it's untreated. So I could make you go do that big, long, complicated equation. You have all the information that you would need. I'm going to talk it through with you, and I'm going to tell you all of that just because. Let's look at our compressive resistance equation. We know that we can pull off our FC and all of these KDs. Let's go take a look. It was an 89 by 89 post. So anything with a dimension 38 to 89 is the smaller dimension. Well, it was 89 by 89. So that is any of these with a larger dimension of 89 or less. So that could be structural light framing or a light framing. But it said it was a number 1 or a number 2 material. So that leaves this category here. So we'd be looking at structural light framing, or basic housing framing, essentially. So let's look at this. Our very first chart was specified strengths and modulus of elasticity for structural joist and plank, structural light framing, which is the one that our grade category said we were, and stud grade categories of lumber. Well, we had SPF, or spruce pine fir, number 1, number 2, right here, and we're talking about something in compression or parallel to the grain. We'd be able to pull off 11.5 MPa as our FC. I told you that standard duration is all you'd ever have to worry about, so 1 would be our KD. It's not part of a system because it's not a joist or a stud, it's a post, so our KH would be 1. Service condition. It was inside, so it was dry, so we'd have a KS of 1. Treatment factor. There was nothing to lead us to believe it was treated, and it was inside, so it would be weird to treat it. So our dry service condition for untreated lumber, 1. Size factor. Maybe there's a size factor. Oh, actually, look, it's an 89 by 89. It looks like we'd probably need to do that equation for it. So we know our 0.8. We know that we can calculate this capital FC. That was 11.5 times 1 times 1 times 1 times 1. So we've got our 11.5. Cross-sectional area, 89 by 89. KZC. We know we could calculate this. They gave us a height, and they didn't say anything about it being braced. So we know we could go through that and find our size factor. And then we know we could plug all this in and find our PR. Except, so you can go do that. If you are interested in it, do it. See if you get the same result that we're going to look up in these charts. Because you have the ability now, I've given you all the information to manually do that calculation. I'm not going to make you manually do the calculation, but if you like math or you like to practice things, go ahead and do it. But I am going to give you the tables. If you go to your downloads, and it's actually in your wood module as well, you can pull up the compressive wood tables. So let me just pull this up, see if it'll let me bring it up. Here we go. And on page 19, oh, that's the wood bending ones. Let's go to our compression tables. I'm already on page 19. Perfect. Well, they said that we had a 89 by 89 SPF number 2 post. So in those charts, I found the page that had a post that is 89 by 89 for sawn lumber, spruce pine fir. Oh look, they've lumped number 1 and number 2 together, and they said our post was 2.6 meters tall. Well, they've given us for a length of 2.5 and a length of 3. We come over here, we can pull off that the PR is 38.2 if it's 2.5 meters tall, and 26.2 if it's 3 meters tall, and we can figure it out linearly between those two. So we've pulled off those two values. Let's come back. Here it is actually pulled off. You can actually see it highlighted in an excerpt of that table. So here's what we pulled off. At 2.5 meters tall, CR was 38.2. And at 3 meters, it was 26.6. We can interpolate for our 2.6 meters tall. If we go through that interpolation, you've seen me interpolate a bunch of times. I'm not going to go through the calculation. You can replicate this if you want. For something that is 2.6 meters tall, we get a CR of 35.9 kilonewtons. So for an 89 by 89 wood post that's 2.6 meters tall, and it's a spruce pine fir, number 2, untreated, inside, we have a CR of 35.9. You can see there are a lot of variables there. You can manually do that calculation if you want. You should get the 35.9 as well. And I know because we do it in the grad class, you actually go through that calculation and get the same answer. So that was our compressive design. Let's look at the same thing for bending design now. Again, you're not going to have to do the calculation, but you can if you want. I'm going to give you an example where we go through and we pull out those values from the bending charts. But you can manually do the calculation if you like to practice things. If it helps lock it in your head, that's the way I am. I like to do examples to lock it in my head, but I like to give you all the background information and then the opportunity to do the math if you'd like to pursue that further. So again, we've got a reduction factor right here. The material reduction factor is 0.9 for wood. Our capital FB is the bending strength incorporating all of the factors. So here's our lowercase fb that we would pull off those charts and then we've applied our KD, our KH, our service condition, but for bending, and our treatment factor. FB, again, what we've pulled off the charts. KD is duration, KH is system, KS is service factor for bending. For stiffness, we actually would pull off the KSE. And I'm going to show you that it actually even comes into play a little bit in the bending, but that is the service factor for our modulus of elasticity. And then KT is our treatment factor. S is our elastic section modulus. Remember, for rectangles, I showed you that it was BD squared divided by 6. We don't have a plastic zone in wood, so we'd never get to use Z or our BD squared divided by 4. It would always be BD squared divided by 6. So we can calculate that if we know what the size of our member is. And KZB is the size factor in bending. Remember, that was a chart for bending. We can go pull it up. And then KL is our lateral restraint factor. Well, remember in our steel belt bending, when we put an object into bending, the top chord is in compression, and compression likes to buckle. Our top chord would try to buckle if it wasn't braced, and so we would need a lateral restraint factor. Most things were actually fully braced at the top, and the same is going to be similar for wood. In fact, in wood, they don't even make us calculate it. They say, hey, did you put a bunch of nails in? Did you connect it to something? Yeah? Okay? Well, then you don't have to bother with that calculation. I'm not even going to show you what it is because it's almost always 1. I don't even want to waste your time. It's almost always 1. Shear design. Again, you don't have to use this equation. We've got our reduction factor for shear at 0.9. FV is our lowercase fv, or our specified strength and shear from those tables, with our different factors applied for duration, system, service conditions, and treatment. AN is the net cross-sectional area. Remember, for steel it was just the web, but for our wood it's its full cross-sectional area. KZ is the size factor, and then look, 2/3 of the area. Remember, for our steel we used 0.67 in our shear as a modifier. Well, that's the same thing here. 2/3 is 0.6667. So it is almost the exact same equation. So look at this. Here's our wood equation for bending and shear. We've got our reduction factor. We've got our strength with our modifiers or our factors applied to it. We've got a shape property. We've got our size factor. And then for strength, we've got buckling. Steel looks like a bit of a hot mess. But if you remember, for shear, we've got those the same. We've got our area. And then FS had that 0.67 applied to it. So for both of them, for bending, we've got a reduction factor, our strength, our section modulus, and then factors for whether it's wood and its buckling capability. And for shear, for both of them, we've got our reduction factor, our strength, 2/3 times the area, times some factors. So whether it is wood or steel, the equations are fundamentally the same, even though they look slightly different. The exact same philosophies are being followed for both methods of material analysis. Again, I'm going to give you an example where if you want, you can go do the math, but I'm then going to give you the tables where you can look it up. So determine the shear and bending capacity of an SPF number 1, number 2, 38 by 184 at 16 inches on center. Well, a 38 by 184, let's just take a look. 184 is 7.125 inches, so that sounds like we're talking about a 2 by 8. Or an SPF number 1, number 2, 2 by 8 at 16 inches on center as a floor joist. It's a conventional house with plywood floor sheathing, so it's a system too. It's that standard construction where we've got something on top that if the plywood tries to go down with it, it's going to engage the ones beside it just a tiny little bit. Let's go way back and take a look at this. Again, you don't have to do this, but if you're interested, we had a 2 by 8 or a 38 by 184 that is SPF number 1, number 2. So let's look. Well, we're in the 38 millimeters, the smaller dimension. The larger dimension was 184, so it's not this. It could be this, but it's not a stud grade. We're not our structural light framing, which is what our last one was, our compression member was. Larger dimension, 114 or more. So we have 38 by 184, which is greater than 114, and we had number 1, number 2 grade. It looks like we're a structural joist and plank. Oh, look, they literally called it a joist in the example. Seems to make sense that we would use whatever strength table gives us information for structural joists. Well, the structural joists and plank is on the same table as our structural light framing, so it looks like that's where we can pull out our information. They said it was spruce pine fir, or SPF, number 1, number 2, and we care about bending and we care about shear. It looks like we've got 11.8 MPa for bending and 1.5 MPa for shear. Remember for steel, for both of them, it was 345 or 350, depending on if it was hot rolled or cold rolled. But for us, there's a wide variation even in the shear and bending, let alone the fact that it is this specific piece of lumber. So with that, we'd be able to look at our load duration factor. I've already told you, 1. System factor. Well, this one is part of a system. We're in bending or shear, and I've told you straight up in the example that it was visually graded as a case 2. Looks like we get to increase the strength by 40%. It's an interior condition, so our service condition would be 1. And it's not treated, it's inside, it's regular lumber, so our treatment factor would be 1. Size factor, larger dimension of 184, this was us down here, and a smaller dimension of 38 to 64. It looks like we would get to apply 1.2 increase or 20% increase on our strength because of its size. It's small, which means we can see if there's any flaws happening on this material very easily. So we get to increase the strength by 40% because it's part of a system, and we get to increase the strength by 20% because it's visually stress graded lumber that's on the smaller side, so they would have seen if there were any major flaws in it. So we could have plugged all of that into these 2 equations if we felt like it. But instead, we're going to go to the sawn lumber charts. Let's actually bring that up for you so that you can see it at a glance. Let's go to the wood bending tables. And on page 31, we have joist selection table for sawn lumber, 38 millimeters by, well, we need to know what, they said number 1, number 2. So number 1, number 2, and we're spruce pine fir, and we're a 38 by 184. We can come across here. They've given us a single member, which means it's not part of a system, or a system case, which we are. Well, that looks like MR is 3.83 and VR is 10.6. So look at this. 38 by 1.84, system 2, 3.83, and 10.6. You can manually do this calculation if you feel like. All the information is there. You can go through it if you'd like, but you don't have to. You get to use the sawn lumber or the bending tables chart. There's glulam in there as well, as much as we haven't talked about glulam. The premise is the same, but I'm not even going to, there's slight variations in the equation, so don't worry about it. I have given you capacities in this chart as well. If we look at these charts, let's make it big. Let's just bump around a little bit. lots of other information in here. So here are beam selection tables for sawn lumber. Here are beam selection tables for glulam as well. So there is the ability to look at glulam elements as well as basic sawn lumber elements. If for example, you had to look something up on a in an example in your assignment or in an exam, it's good exam questions. Okay. So here we are. This is what we looked up. We looked up our 3.83 and our 10.6. Now we did that example 2 weeks ago with steel, where we had this canopy. It was an existing building where we calculated the snow load, we calculated the dead load, we figured out what the tributary width was. We looked at the loading, we found MF and VF, and we found CF on the column. And then we figured out if the architect's request for a specific column and a specific beam worked. And then we gave them feedback on other alternatives that might actually even be cheaper than the ones they're looking at. Well, the architect wants to investigate wood construction. Turns out that when they got into the existing building, it was a mass timber project, or it was an existing project back when they used to build with wood before. And they kind of want to match the aesthetic of the existing building. So they want to look at they want to at least investigate what it would be like with wood. So they want to know now for the corner post, what size do we get from the sizing guidelines? Does a 140 by 140 Douglas fir number 2 work? So that's a 6 inch by 6 inch Douglas fir. Remember, it's really 5.5 inches by 5.5 inches. And then they say, is there anything else we should consider? Is there anything else we should stop to think about there? And then, what is the best square column? Maybe it's this one, maybe it's not. Let's take a look and see. So, if we go to our song, sorry about that, the recording feature froze, so there was an abrupt stop for you guys. As I was saying, if we go to the wood compression tables for all of the different compressive elements, let's go to, I already know it's page 33. So let's jump around. You'd want to scroll through and find this, but column selection tables, sawn lumber, Douglas fir number 2. That is exactly the things they talked about in the question. 140 by 140. They've told us that it's 4 meters tall. Well, look at this. 4 meters, 140 by 140, 68.4. Let's come back and take a look at our chart here. That matches what I've pulled off in this example so that you can just see it easily. We've got our Douglas fir larch number 2, 4 meters tall, and it's a 140 by 140. Gives us a PR, or a compressive resistance, of 68.4 kilonewtons. Oops. Now, it said, is there anything we should consider? It's outside. This chart is for dry service conditions. They don't have a chart for wet service conditions. We know that it doesn't get applied to the whole equation because buckling, it doesn't apply it to the buckling component, it just applies it to the strength. So we can't just take that same factor and just apply it now, but we know that the wet service conditions might have an impact on the strength of this. We would possibly need to manually we would manually calculate this now. You can, if you feel like it. I would accept for something like this saying that the 140 by 140, that this is the value. If this is greatly larger than our factored load, I think that's fine enough. We know that the reduction factor for a wet service condition was like in the range of 80 to 90%, if it even had a factor applied to it. So if this is a lot greater than our factored load, I'd be okay with it. One of the other things they said, does anything else work? Well, the only other thing smaller than a 6x6 is a 4x4. And if I go and look at a 4x4 for Douglas fir, whether it's select structural or number 2, it doesn't work. Do you guys remember that our factored load, because it's the same factored load, none of that changes. Our factored load was 23.2 kilonewtons. We calculated that 2 weeks ago. All of that first part of our analysis stays the same. Our tributary width is the same, the loads are the same, everything stays the same. So just a reminder, the beginning part was the exact same as our steel example. So I'm not going to go through it because we did this. We had our dead load as 0.76. Our snow load was 1.44. We applied our different load factors and we found our worst case is 3.11. Sorry. I don't know what he's talking about. Sorry, guys. Sorry, my husband is pulling our boat for the winter. And the place where he takes the boat has a gate across it. So he got up, we both got up at 4 this morning so he could drive up north and pull the boat from the water. And then he's pulled it and the guy isn't there to accept the boat. So I don't know what I'm going to do. Go for it, Dave. Okay, the tributary area on the column, same as the steel calc, 7.5 meters squared. The load on the column is our load, our factored load, times our tributary area, 23.3, I said 23.2, I remember, pretty close, 23.3 kilonewtons. So, step 1, they said sizing guidelines. Well, our height divided by 30 gives us 133 millimeters. Well, a 6x6, pretty darn good. 140 by 140 seems like a good estimate for our column size. They wanted to know, did the 140 by 140 Douglas fir number 2, that's 4 meters tall, work? Well, we calculated, or we looked up a CR of 68.4 kilonewtons, and CF was 23.3. It works. We know that it's outside, so it's wet, so that CR would actually be lower than that, but seems like we've got lots of capacity, like 3 times the capacity we need, pretty much. So I think I'm comfortable saying that that works without going through the full calculation. They wanted to know if there was something we could get that was smaller. So we looked at an 89 by 89 Douglas fir select structural, but even not wet, the capacity was 18.2. It would be less than that because it's a wet condition, and that's less than our CF, or the reduced capacity is not greater than our factored load. So we couldn't use an 89 by 89. So it looks like the 140 by 140 Douglas fir number 2 is the best choice if they wanted to go with the wood option. So now they're doing the same thing for the beam. So you remember the beam we designed in steel 2 weeks ago. They want to know if a 140 by 343 Douglas fir number 1 would work. If we use that in place of the steel beam, would that work? So what size do we get from sizing guidelines? Does that work? Is there anything we should consider? Yeah, it's wet, it's outside. Whatever it indicates as the capacity isn't going to be the exact same. And what is the best Douglas fir beam? Remember, the smallest one is going to be the cheapest one. So is there something smaller that works? Because that's going to be the cheaper one. We usually pay for things based on tonnage quite often. So if we go to our handy dandy wood bending tables and go to, you could flip through the pages. I'm going to go to page 55, and it looks like I'm already on it. Sawn timber, 140 by something, and we have Douglas fir, and they said that there's select structural, number 1 and number 2, so we were number 1, so we're going to be in this chart, and we had a 140 by 343, so right here, if we come across, MR is 39, and VR is 43.2. Look, they give us something to do with I here. I can tell you that if I was mean and made you worry about deflection criteria for wood, you would have to pull off what that is. Because the E is a bit of a pain in the butt, they lump it over into the look it up side, but it's the same premise that we would have done with steel. But I've only asked you to look up MR and VR, so 39 for MR and 43.2 for VR. We know that it's wet and it's outside, so those might not be exactly right. So look, you can see we've pulled off that information there. So again, the load, MF and VF, same as what we found for our steel one. So MF of 35 kilonewton meters and VF of 23.3. A sizing guideline would tell us for a wood beam, and this is a standard wood beam, and if we looked at that drawing, it is doing the job of a beam. Its length divided by 14. Our length was 6 meters, so 6 divided by 14 gives us 429. Those tables, let's come back to those tables for the 140s. They only gave us up to a 394. So that makes me think maybe we'd want to switch to glue lam, or maybe we'd want to, no, even this, the deepest member was 394. Let's look on the next page. Maybe there was more. Doesn't seem like there's much options. So based on the sizing guidelines, this says, probably not. You probably don't have something that works in our sawn lumber. You might want to go to glue lam, or steel might be your final answer. So this would be at a very preliminary stage. That you'd want to start getting it into your head that sawn lumber might not work for this. But they've asked us now to actually investigate it. They said, we understand it might not work. We've left an allowance for glue lam in our preliminary design. Is there a way we could get it a little bit cheaper and have it work as sawn lumber? So we went through and we looked at the tables and we saw that MR is 39 and VR is 43.2. Well, MR is greater than MF and VR is greater than VF. It's outside though, it's wet. MR and VR are going to be slightly less than this. We have some extra capacity here for MR, but it might be tight. We might need to not rely on just the tables. We might need to go through and do a rigorous calculation. You guys don't have to. This is the feedback that I would give the architect at this stage and say, based on, well, at the very preliminary stage, the sizing guidelines would have said probably not at all. Now that we're at the kind of more rigorous design, I'd say, it's tight because it's outside. Are you sure you want to go this way? And if we want to go that way for wet, it's exposed. This thing's visible. Let's take a look at what it might be if it was select structural instead. So let's go back to those two tables. here's where we pulled off our 39 and our 43.2. If we went with select structural, the values are pretty darn similar. So yeah, select structural is going to cost more, but we have less lumber, and select structural looks nicer. Often we like select structural because visually it is the nicest. And often architects, if the lumber is exposed, will choose select structural anyway. So that's feedback I'd give them, that it might work as a 140 by 292 or a 140 by 343, depending on if it's a number 1 grade or select structural. But it's outside. We might need to do a bit more investigation. Do you want us to pursue it? How important is this to you? I can tell you that I've done the calculation, and both of those actually do work in the wet situation. If you wanted to, you could go do it too. All the information is there. In fact, we talked through some of it with the last example. So you could go through and see if it works for a wet condition. So that's the feedback that I would give the architect at that point. Now, just for graphics, I gave you a little kind of illustrative example here. This was the post for steel. That was the cheapest that worked. This is the post for wood. That is the cheapest that works. So that was our 64 by 64 versus our 144 by 144. These are very loose numbers. Here's the weight per meter, or a mass per meter, I guess. Almost 6 kilograms per meter for the steel and almost 11 kilograms per meter for the wood. And the prices are very similar. So it seems like this would be a purely aesthetic choice at this point. What does the architect prefer visually? For the beams, we've got a shallower 200 by 18 for the steel that weighs 18 kilograms per meter. It costs about $120 per meter. Again, very rough numbers based on these weights. Our wood is bigger, and yeah, there's a premium on the steel, but this seems like these were very rough numbers. Would we switch this to the 140 by 291? That's select structural, and maybe this cost goes up. It's hard to tell. This is the feedback, again, I'd give the architect and say, at this point, both of these seem like valid options, depending on what you do for the columns and what the main building is. Here's your feedback. I think the aesthetics are going to be what govern the choice at this point. Let me know what you choose, and I'll update my drawings accordingly. So that's the end of wood. We can now look up or calculate the capacity of all of our wood members. You should really get it into your head that wood is dependent on environmental conditions and the fact that it is an organic material, that we have lots of variability in its capacity. So you should have some general knowledge about wood, a lot of those things that I talked about. Remember, everything's open book, so you can always go back and reference. You should know the main factors that impact the strength of wood, and you should know how to use the beam and column tables to look things up. Those are going to make fantastic exam questions to look those things up, maybe possibly even interpolate between two things. So that's the general information on wood. Next week, we're going to start talking about composite material and what's load sharing versus composite. And we'll need to know that because we're going to start talking about concrete as well, because concrete's the last major material that I want to talk about with you guys. So that's the end of our wood lecture, and we're getting there. And I think this next week is reading week for you guys, so there'll be no new lecture next week. We'll jump back into it when you guys come back.